Well, hello there. All right, today we're going to cover really one of the final things that we're going to talk about concurrency-wise using Python. There'll be some other topics that we're going to cover here to finish up the semester. But today I want to talk about event-driven programming and async I/O, which is part of a way of doing event-driven programming in not just Python, but other languages as well. So let's go ahead and dig into that. So first off, we've been looking at concurrent systems and concurrent solutions to problems, and we've been doing that all semester. And we've looked at both using threads, which are kind of all within one process, and the process itself switches between the threads of execution. And we've also looked at using processes, where the entities are completely separated and isolated from each other in their own respective processes, and those processes might even be on different machines. They might not even be in the same CPU or same system. They could be something more like a cloud-based system. And we've looked at getting those threads and processes to synchronize and communicate. And our concurrent solutions using either threads or processes, there was non-deterministic behavior that showed up when we executed any of those concurrent solutions to things. But they still generally followed a flow of execution. In other words, this happens, and then this happens, and this happens. And maybe you have two threads doing that, where they're each doing things. And then we controlled that with synchronization. Lock here to stop the flow until this thing unlocks it, and then allow the flow to proceed. So a typical programming solution, as we've seen in what we've done so far, looked something like this. So we had, for example, sequential. Start, A, B, C, D, E, and then end. So that's totally sequential. But then a concurrent solution might have had the sequential part here, and then we farm that out into three threads, B, C, and D, that all run concurrent with one another. And then those threads or processes complete, and we use a join, and then we're back to doing something sequential at the end, and then we stop. So note in this concurrent thing here, it doesn't matter if these are threads or processes. It's really the same because they're just running concurrent with one another. The only difference between threads and processes here would be threads could share the same process space and the same global variables. Processes would be more isolated from one another, and we'd have to use some sort of communication mechanism or inter-process communication mechanism in order to get them to share data. Now, event-driven programmings, however, can still have elements of concurrency, but they usually look different. In other words, we usually have an event loop that when events happen, they go into that event loop, and the event loop then processes that. So those incoming events determine and how they're reacted to determine what the program will do and when it'll do it. So notice that's a little bit different than the kind of flow that we would see with a program like we had back here. That in an event-driven program, you basically have a main program that's waiting for events. When events happen, they get handled in some way. It causes some code to be executed when that event occurs. And you might note that those events are usually from some outside source, something happening. And they could come in any order. So the program has no real way of knowing what event will happen next or when a certain event will happen. So notice there's some elements of non-determinism there that come from the fact that it's an outside force causing those events to happen. And you've probably seen this before in written programs that are kind of event-driven. So an example would be if you've ever written like for those of you that are in the gaming degree, if you've written a Pygame program, then you usually have some main loop that does pygame.events.pump, and then you get an event comes in like from the keyboard or a mouse click or the window being resized or moved or whatever. And then we write the code that says, hey, when this key is pressed, we take this action. When this key is pressed, we take this action. So we extract an event from the event queue, and then we have some sort of if statements or some sort of way of processing those events to do what we want to do when that event comes in. Now, you also maybe are used to this with any Windows graphical user interface program that you're using. You have a window. That window processes those incoming events, and those incoming events come from keyboard, mouse, window changes, minimize, maximize, redraw, load, exit, etc. So a lot of GUI systems are built on this model of event-driven programming, Windows included. And in a Windows program, it's important to note that every window has an associated event queue. In other words, as events come in, they get built up on this list, and it's up to the programmer then to write the code that pulls an event off the event queue and then does something about that, handles that event in some way. So events will generally be handled by the application one event at a time, and the code that handles the events is what we would call the event loop. So here's, for example, a typical Windows program. You have all of these possible input kinds of things here: keyboard, mouse, timer, window manager for resizing windows and minimizing and maximizing and Xing out and so forth. So all of those things feed in. The operating system then decides, hey, they pressed a key. What's the current window that's on top right now? What's the one that has focus? And that's the one that this puts the events into that event queue. And so that's how the operating system sorts out. You can type in your word processor. You can switch over to a web browser and type into that. You can switch to a different tab and type into that. That's how it sorts out which events go to what thing. Is the window manager of the operating system does that. And then in the application itself that we write, we basically just say, pull an event off the event queue, do something with that event, process it in some way. And we just repeat that over and over again. And you may have seen programs, well, actually, I'm sure that everybody in here has seen a program where Windows says, hey, this program has stopped responding. Do you want to kill it? And what happens there is if the event loop, for some reason, locks up, or we enter an infinite loop inside of here, or get stuck or blocked inside of here, and then we don't keep taking the events out of the event queue, the window manager notices. It's almost, you can think of the event queue as like a mailbox. And when that mailbox fills up, and the operating system keeps looking at the mailbox and it puts more events in and more events in, and none of them are being pulled out, it says something bad happened at this house, this application. Whoever was there is dead, and I've noticed that because the events have backed up and nobody's processing them. So the event queue, if that locks up, that's when you get that message, hey, this program is no longer responsive. What do you want to do about it? Okay, so the flow and event-driven program doesn't have that kind of flow like we had before. It basically has something that looks more like this. So we have our initialization code, and then here, rather than concurrent stuff, we have a wait for some event to come in. And when that event comes in, we handle that event. And this star here means we're going to do this 0 or more times. We're going to do this over and over and over again. And then until the program is ready to exit, and eventually we'll get out of the event loop here, and then we will end and clean up things at the end of the program before we terminate. Now, one thing to note is that the wait there, and then followed by the handle code, is going to repeat indefinitely and is usually ended by some event that causes the loop to exit. So, for example, you click on the little X in the upper right corner of the window. That sends an event that basically says, hey, I want to close this window. And then the program can then say, oh, well, I had this while loop that was running. Let's break out of that loop because they said they wanted to end the program. And you might also note that the number and type of events can be small or can be very large. We could have only a few events and we could ignore events. We could say, hey, I don't care about mouse events in this program. Or you could care about all kinds of events and write handlers for all of them. So it's up to us as the programmer to set up this event-based structure like this. Now, the idea here is that this method of program allows us to think of solutions in terms of a set of possible events that could occur, and then how we want the program to deal with each of them when they do occur. And the idea there is that is especially useful for certain types of systems, like operating systems with a GUI interface, games. When this thing happens, this action gets taken. When the player clicks here, the player jumps. You can think of those as events that are then being processed in some way. You could also think of like automotive systems. When the seat belt gets disconnected and the car is in drive, start beeping the thing that causes it to beep. Or the running of the engine itself could be thought of as sort of an event-driven system. When the camshaft gets to this location, then cause the sparks to fire in these cylinders. And when it gets to the next position, fire different cylinders, open these valves, and so forth. Now, a lot of that is mechanically done, but it's still, you can think of it as a sequence of events that are kind of self-sustaining. Industrial control systems as well. When this gate on the CNC machine gets open, shut down the spindle because somebody has opened it and it's not safe. Or the conveyor belt, when an Amazon package comes along and it has this barcode on it, it gets sorted onto this other conveyor belt. That's very much an event-based system. So to write code that way, we basically need to think of all of the events that could happen, and then we need to write a handler for each of those events. So when this event happens, we do this. And notice that's different than a typical program flow, because we can't control when the events happen because they're usually coming from an outside source. There is no flow that we do A and then B and then C and then D. It's more like, oh, event, keyboard pressed, A happened. What do I do about it? Mouse click, event happened. What do I do about it? Now, that type of programming is a different way of thinking, and it can also create some difficulties. And the reason for that is because we can't control the order that those events are going to happen. We have to be a little bit careful about that. It also offers us a way of writing and controlling solutions that have concurrent elements of execution, but only use a single thread. In other words, by an event-driven system, you could say, hey, when this timer ticks, I carry out this action. When an event click, mouse click happens, I carry out this action. Of course, those actions have to be relatively small and simple, but it does give us this method of doing that. Now, one of the things that I want to talk about today is this Python module called asyncio, and that stands for asynchronous input-output. And what the asyncio module does for us, it's a library to write concurrent code using this special syntax called async and await. And that is particularly useful for writing a single-threaded system that still allows concurrent code to be generated using coroutines. So in other words, rather than going to the complexity of a full-blown concurrent solution with multiple threads, this allows us to have one thread, but still have start certain events or certain processes, and then when those have a result, then we can handle those later as an event. So rather than having to say start this process or this event, this action, and then wait for it to finish, and then start the next action, wait for it to finish, and start the next one. You could say start all of these, and then as they finish, we associate some sort of event handler code with those things when they're done. So the asyncio module basically provides the infrastructure for doing that, for writing those single-threaded concurrent solutions that use coroutines. And what a coroutine is, it's like code that can be running at the same time, but not in a separate thread. It's usually some sort of input and output with a network socket or some other hardware resource. You have multiple clients connected to your program. When you got, let's say, 10 clients and you're logged into your online multiplayer game, rather than having 10 different threads, you have one thread and said, hey, when I get a packet from player one, I do this, and I send this message out, and I wait for a response. When that response comes in from that player one, I do this, but I'm also have requests going out to player 2 and 3 and 4 and so forth at the same time. So it allows us to do that kind of thing, and it has primitives that are related to helping with that. So async IO is usually a really good fit for IO-bound, high-level structured network code where you need to do something across a network, wait for an answer to come back, but you don't want to just be stuck there waiting. You want to have multiple ones of those going at the same time to different clients potentially. Now, I highlighted on this slide that single-threaded concurrent code using coroutines. So let's dig into that a little bit further. So the asyncio module itself provides kind of a set of APIs that are both at the high level of abstraction and then a lower level version of abstraction. So the high level async IO APIs essentially allow us to run and control Python coroutines. So it allows us to create these coroutines, execute them. They also, the high level ones, perform network IO and interprocess communication for us, allow us to control subprocesses, distribute tasks via task queues, kind of like event queues like we talked about earlier, and then also synchronize the concurrent code, this async IO concurrent code. Now the low-level APIs, what those do is they allow us to kind of create an event loop, which provide APIs for networking, running subprocesses, handling operating system events and signals, and so forth. And it also gives us the ability to implement the efficient protocols using what we're going to call transports, and we'll talk about that later. But there's also this callback-based libraries that are in there, and it allows us to bridge between callback-based libraries with code that uses the async and await syntax. And this will make more sense here in a second when we take a little closer look at it. Okay, so the async IO event loop essentially works like this. The core element is an event loop, just like we talked about in Windows, where there's a loop that processes events as they happen. So the event loop is essentially responsible for scheduling and running those asynchronous tasks. And then it also handles any asynchronous IO operations and also any subprocesses or coroutines that we have. So the event loop that we have is related to the events that happen due to any code that we have that's active in our current code scope that's using the async and await feature on any action that is what's called an awaitable action. In other words, something that can cause one of these events that we could wait on. Okay, so what are awaitable items? Awaitable items are anything that can be used in an await expression in the language. So there are three main types: coroutines, tasks, and then what are called futures. So we're going to take a look at each of those one at a time. So let's go and start off with coroutines. So coroutines, they're a special type of function that's awaitable. In other words, it's a function that has a, just like any other function you would make in Python, except that rather than using def to define it, you say async def in place of the usual def when you define the function. So in other words, you just add the word async at the beginning of that function, and then it becomes a coroutine function. And an object returned from a coroutine function is called a coroutine object. Makes sense. All right, now, tasks, on the other hand, those are used to schedule coroutines to execute concurrently. So these are, notice there's a hierarchy here, that tasks will schedule coroutines. In other words, you might have a task that creates those coroutines and launches them to schedule them. And so we'll need to make at least one task that will run the event loop, because it's the thing that's going to be handling those processing of those events as they come in. So there's usually at least one main task that will be started. There could be more than one, but tasks are started by passing a coroutine to asyncio.run, and we'll look at that in more detail in a second. That'll make a little more sense here shortly. And what a future is, so those are the three parts. So we have coroutines, tasks, and futures. So a future is a low-level object that's awaitable and represents the result of some asynchronous operation that will eventually be produced. So the idea there is, think of that like an order that's been placed that will eventually be filled. So you might think about a restaurant where you order your food. They stick the food ticket up on the little counter thing. There's a little spinning thing. The cook spins it around and they look at it and they make the stuff. It's not immediately available, but eventually it will be. And when that is done, they put the plate up on the thing and they hit a bell, ding, and say order up or whatever. And then that's associated with that order that was up there. Now, you might note that there might be multiple meals being prepared all at the same time, and they're going to come up at different times. They'll become available at different times. So futures are kind of a way to track and handle expected future results. In other words, you put an order for, I don't know, like something at a restaurant, like a chicken breast sandwich or whatever, and you expect that in the future they're going to fulfill that order. So futures are a way of waiting for those things that we know are going to happen in the future, and then when they do happen, handling them. All right, so here's a simple example. And this example is somewhat trivial. I mean, it's only a few lines of code here, but I wanted to make sure that you understand what's going on. So the first thing we need to do if we're going to use async IO is we need to import it. And after we import that, we can now use the async keyword. So notice this looks just like a Python function, but there are a couple key differences here. One is we put async in front of the def, and then the second one is we have an await in here. So we're saying await async IO.sleep delay. So this is going to pause the execution for a certain amount of time, and then after that amount of time is done, we're going to have the message get printed. So this is like printing in some amount of time into the future. And notice we pass in the message we want printed, we pass in the delay of how long we want before it gets printed. So now we do an async IO.run, and we're calling the future print function, which since that's an async function we're allowed to do, we pass the stuff to it. So this is going to pass in the delay, which means 1 second in the future, this thing's going to print out that message. So async IO.run, async IO.run. So this is a test. It's going to show up 1 second later, and then 1 second after that, or 2 seconds later, we're going to get goodbye printed. But one of the things to note is that these are really running at the same time. So that previous example seems trivial. It simply executes one function call and then the next. And really, there's not any concurrent behavior happening there. I was actually a little bit wrong about that. That this is going to happen 1 and then 2 seconds later that, because this is going to be async IO.run is actually going to run this one first, wait for it to finish, and then the async IO.run here is going to wait for that to finish. But these are still going to delay, so it's going to take a total of 3 seconds. 1 second we get this is a test. 2 seconds later we get goodbye. Now to run those coroutines concurrently, so that those two future prints concurrently, and kind of coordinate those events, there's some additional features to async IO that we need to look at. So async IO.gather takes a sequence of awaitables, returns an aggregate list of successfully awaited values. Async IO.shield prevents an awaitable object from being canceled. So in other words, you can say don't allow this to be canceled. Async IO.wait waits for a sequence of awaitables until the given condition is met. Async IO.waitFor waits for a single awaitable until the given timeout is reached. And then async IO_as completed. It's similar to gather but returns futures that are populated when the results are ready. So notice that you could use async IO as completed, and that's like kind of like pretend that those are done, but allow the futures to be filled in later on. So here's a concurrent example that's the same as the one we had earlier. We have async def future print, just like we did before. There's no difference in this function. But now I've created this async IO or async def main, and what it's doing an await async IO.gather. And if you remember what gather did, it takes a sequence of awaitables and returns a list of successfully awaited values. So in other words, it's taking rather than just one of these, it's taking a sequence of them. And here we have two, future print that, and it's starting them at the same time. In other words, these are now concurrent. And then we do async IO.run, and we're running, in this case, this function, this async function main, and it's going to be overlapping these. So in other words, both of these are going to be running at the same time, waiting for their event to finish. And in this case, it's event driven. So the first one that's going to generate the event saying, hey, I'm done, it's going to be, this is a test, because that's 1 second. And then 1 second after that, we'll get this goodbye that gets said that it's done. So these are going to be happening concurrently. Now, one thing to keep in mind is that await can only be used in a function defined with async. In other words, you cannot use await in a normal def function. It has to be an async function. And you'll also note in that previous example, both tasks are scheduled to execute in the event loop. so that the execution is overlap. So both tasks, meaning both of these future prints, are both overlapping. So they're concurrent with one another. But unlike with threading, instead of it switching between them, do this, do this, do this, do this, it's using what's called cooperative multitasking. In other words, it only switches to the next task when it's waiting for something. So in other words, think of it kind of like again, the cook, that they're like, they pull down one order and they start working on that. And rather than them just saying, I'm partway through this task of cooking this grilled cheese sandwich or whatever, I'm going to switch and start doing something else, or be pulled off of that and be forced to start something else. They'll say, when I get to the point where I have the grilled cheese on the skillet and it's timing, while I'm waiting for that time, I'll start some other process. And when they get to a wait point on that other process, they'll switch to the next one, and they'll eventually cycle back around to the grilled cheese again. And the grilled cheese might have, if they're waiting for everything, the grilled cheese would have a timer. It goes ding. They say, oh, I got to get the grilled cheese off of the griddle. And so the idea there is that's how cooperative multitasking works. In other words, rather than a thread where it's just do this for a while, do this for a while, do this for a while, it's like do this until we have to wait, and then do this until we have to wait, and then do this until we have to wait. So let's look at a use case that's a little more practical than this kind of future print thing we did over here. All right, so here's a case where that's like the lab we did before, where we downloaded a bunch of pictures. And in this case, you'll notice that we want to download multiple files, just like we did in that previous lab where we downloaded the NASA images. And those multiple files, if we did it sequentially, it would look like this: get file F1, get file F2, get file F3, and so forth for all of them that we want to get. So that might be something that a web crawler would need to do as well. Get this contents of this web page, and then spider through that and find any links that it links to, and then get the things from that page, you get the things from that page, you get the things from that page. And so you're constantly getting HTML files over the internet. It might also be something you do when you have a bunch of files that you want to download from some site. Download all of these files, download all these attachments. So this is the kind of thing that we might actually need to do. This is a practical example. Now, if we do the sequential version, it's going to end up looking like this. In other words, get file F1, wait for it to complete. Once it's complete, we have that file, so we go on to file F2, wait for it to complete. And we keep doing that until we get to the last file. When it's complete, we're done. So that means each must wait for all previous downloads to complete. So in other words, any F that has a number smaller than the one we're on, we can't start downloading F2 until we already completed that one. We can't start F3 until we're done with F2. It's completely sequential. Now, here's what the sequential implementation might look like. So here, again, are 3 of those NASA images. And we do a download all sequential. We basically start them all. We just go through the list. We get one. Once we have it, we call this download file function down here. We download it. That downloads it and saves it locally, and then we just have a loop that goes through one at a time in all of the ones that are in the list. And you've done this previously in that previous lab, so you should be familiar with something like this. And you'll also notice that I have this download all sequentials returning the time. The time sequential TS is getting returned from that. We capture the time at the beginning. We then capture the stop time at the end, and we return the difference between the stop time and the start time. Now, if we're going to download multiple files using async IO, we could do something more like this, because notice that back here, there's a lot of time we're waiting for this file F1, and that if that's somewhere else on the internet, that could take a while. We have to contact a server. It has to start sending us data. We might have a point where it blocks, where we're not done yet, where we have part of the file but not all of it. So why wait and do absolutely nothing while we're waiting for something to do something? Why not get multiple jobs done, just like the cook in the kitchen? Why not start the the grilled cheese, start the chicken on the griddle, put something in the oven, start the water boiling. Why not overlap those things instead of just sitting there waiting, doing nothing? And so that's what we have here. Is the idea is we use a gather. We say we want to gather all of these files, and then we're going to wait for all of them to complete. And when they're all complete, they're done. But notice that by doing a gather on all of these, we can overlap each of these operations. And when one of them blocks to wait for some event, we can cycle to the next one and process some of it. When that one blocks, we go to the next one. When that one blocks. So the idea here is we start all of them with an async io.gather, and then we just still wait for them all to finish, but it allows us to overlap operations, which can make things quite a bit faster. And it also allows us to overlap it in a way that is not using multiple threads or multiple processes. So we don't have to worry as much about synchronization here because of that. All right, so here's the async IO implementation of that. And let's just walk through this briefly here. So the first thing we'd have is we had the async at the beginning here, def download all async. And we still are capturing the start time and the end time, start time and stop time, and returning that. So this works the same way. But notice what we're doing inside of the loop here is rather than a normal for loop where we just went through all of them, we create this AIO HTTP client session. That's an asynchronous IO network connection, basically, HTTP network connection. So we're creating that client session. And notice we have this task list up here. And then what we do is we go through a loop, and we're not really doing anything with these just yet. We're just adding all of them to our task list. We haven't started it. So before, remember our file download from over here, note that we actually called download file each time through this for loop, and that we had to wait for it to complete. Over here, notice we're just creating our task list. So we create our task list, and then once we're done creating the task list, we do await async io.gather, and then we put all of the tasks here to say gather the results of all of these tasks. And then that starts the process of doing the cooperative multitasking, overlapping all of those operations. When one blocks and waits, it goes to the next one. When that one blocks and waits, it goes to the next one. And so to finish this up, it's continued on the next page. We then have the async def download file async. And we basically just are calling that each time. That's using this await response.read for reading the data, and then we put it into the file to do all that. And then down here, finally, we do the time concurrent async io.run, download all async. We just call this async function up here that downloads all of them. So you notice that those two programs are very much similar to each other. We have a download all sequential and a download file, and then we end up calling download all sequential. Over here, we're doing the same thing, download all async and download file async. So again, parallel implementations. One of them is using async IO and running those as coroutines. One of them is running it sequentially. So this is going to be much faster because we're not just sitting and waiting doing nothing. And it's also can have much less overhead than we would have with starting different threads or different processes to do these things. Okay, a couple notes here. The implementation uses that AIO HTTP module. And like I said at the beginning when we were talking about this, that one of the big uses of asynchronous IO is with web-based systems because you might have multiple clients connected and you need to be sending data to multiple clients and getting responses from multiple clients. And you'll notice that async IO or AIO HTTP module that has asynchronous versions of a lot of the HTTP functions that are in the HTTP module. So essentially it allows us to asynchronously get data from multiple sources at the same time in this cooperative way without the overhead of threading, without the overhead of that. And also because it's cooperative multitasking, where only time it jumps from one thread to the next is when it's waiting, there's less need for synchronization here because they're not really overlapping in any possible way. It only jumps to the next one when it's doing a wait on something from a previous one. So to run that event loop that starts all the downloads, we use async io.run, and then we pass the coroutine download all async to it. And one thing to keep in mind here is that async IO programs, they are using cooperative multitasking. So we can't simply call URLlib request URL retrieve like we did before to get data. And the reason for that is the reason why we can't do that is because since it is cooperative multitasking, that function needs to be written in such a way, this says why not, it needs to be written in such a way so that when we do hit some sort of blocking thing where we're waiting on IO from the thing, we need to have something where it knows how to then switch to the next task. And those functions have to be written, because it's cooperative multitasking, to be written in such a way, where I would have blocked, I switch to another one of the coroutines and let them make progress. So that's why we have to use this AIO HTTP module. Okay, a couple final notes here that Python and async IO is not the only language that has this. Other languages support asynchronous behavior, notably JavaScript. If you've ever programmed anything in JavaScript, makes really heavy use of that. But the reason for that is JavaScript was written to be something of the language of web browsers that are obviously doing a lot of network thing, getting data from different places on the internet, pulling that data in, maybe a web page or a web app getting multiple pictures and images and downloading them. So JavaScript makes pretty heavy use of that. So if you're programming in JavaScript, you should get used to that concept of an asynchronous function call, where it's not like a normal function call where the program blocks and waits. It's a function call you make, and then later on in the future, when that function completes and has the data, it makes the data available to us. Now, async IO can be pretty powerful for handling numerous IO-bound tasks or maintaining responsiveness of the program during long operations that block. So imagine you have a GUI program. You don't want to have it, you click on a button to calculate something and it locks the whole program up for a while. You want to still handle the other events as they come in while something is blocked waiting to complete. And one other kind of final thing here is note that even though asynchronous programming is a form of cooperative multitasking, the tasks are still being executed concurrently, meaning that they can still switch from one task to the next, to the next, to the next, and it's going to happen only when there's some sort of blocking event, but there still might be a need for synchronization and communication mechanisms between those tasks. So async IO in that module, it does have support for the synchronization mechanism you're used to from processes and threads. There's a lock object, there's an event object, there are condition objects, semaphores, bonded semaphores, queues, priority queues, LIFO queues. So there's a ton of support for those things if they are needed. I will say in the times that I've used async IO for solutions, I haven't needed to use things like lock as much because it's cooperative multitasking, and usually the tasks are more isolated or independent from one another. In other words, download all of these files. We don't really care about, it's not like we're accessing a bank account record or something like the ornamental garden problem where there's shared variable. We're doing some task that all of these things need to be done, but that doesn't really, one isn't interacting with the other one directly in a lot of cases. So sort of like a cook at the diner. They're cooking all of these different meals, but the meals don't necessarily have to interact with each other very much. Now, but if you think about that, there still might be a need to say, well, all of these meals go to the same table, so let's get them all done and try to get them done about the same time and then send them all out together, because you don't want somebody getting their food and then eating while the other person is waiting. So you might can think of that as something like a lock. Lock this behavior of this group of things until all of them have completed. So something like that. So I would strongly suggest you investigate event-driven programming and async IO more. If you're ever programming JavaScript, you're going to need to understand that more. And I have a link that I put here that talks about the async IO library. What I gave today was a brief introduction. I wanted to keep this lecture somewhere around 45 minutes. Looks like I've done a good job since we're about 40 minutes right now. But I would encourage you to look at that. And I would encourage you actually to try that example back here, because it's very similar to the one, this one. It's very similar to the one we had done before, and then compare and contrast how that code is written and how it works compared to the multi-threaded, multi-processing version that we did previously. Okay, so that's all for today. Everybody stay safe, and I will see you guys next time. And we only have a few weeks left in the class. There's some more things that I want to get to in here before the end of the semester. I want to get to concurrency in other programming languages. Specifically, I want to talk a little bit about that in a language like C, C++. I also want to spend a little bit of time maybe looking at distributed computing systems like MPI. I don't know if we'll have time to get to that or not, but I do want to spend a little more time filling up those things. And we are probably going to have one more, maybe two more assignments, but they'll be relatively straightforward, I think, relatively small amount of code that you'll have to write. But work on your other labs. Make sure you get those done and submitted. And if you have any questions, as always, shoot me an email, send me a text message. We can always set up a Zoom call. You can share your screen. I can look at your code. I can help you with things. But do feel free and to send me some kind of message if you're struggling, because I really want everybody to do well in this class. All right, that's it. And I'll see you guys next time.